Hello, welcome to my lab 4 on oscillations. So what's the purpose of this lab? This lab's purpose is to model the oscillations of a real-world spring using the tracker and a GlowScript computational model. So the topics discussed in this lab are energy principle, spring force, gravitational force, work, and Newton's second law. Now, Newton's second law states that the acceleration of an object is dependent on the net force and the mass of the object. It is also used to calculate the initial velocity using the velocity and position update formulas. In this case, it's used computationally to model the motion of the spring mass system, and the energy principle is used in the law of conservation. Energy is used to calculate a lot of the values we're using in the code. So our system and surroundings. Our system is the mass, the spring, and the earth, and our surroundings is nothing. Because there's nothing in the surroundings, potential energy is used with no work, as work is zero. So the two values used are the potential energy of gravity and the potential energy of the spring force. The tracker experiment was used to model a video using the spring to model the movement of the mass and then create a position versus time graph as shown on the left side, sorry. So in our code we input the mass of the ball, the original position vector. We also input a calculated value of the spring constant and then the relaxed length of the spring, which is L naught. And then we input the F net, L hat, S, and then all the energy changes in order to output an accurate computational model as well as an accurate observed model. So for finding the spring constant and relaxed length, for the spring constant, we use the period of oscillation formula. Using this, the period of oscillation, which is T, is equal to 1.52, which was experimentally found. Using that, we figure out K from using algebra, which is 6.87 newtons per meter. And the same side of the coin, we use L naught. We use the energy change formula. So we use mg is equal to K of S, which is L minus L naught, to figure that out. And then we find that L naught is equal to 0.1261 meters. So the model and experimental values are similar in the y direction, whereas there's a lot of variation in the x direction over time. In the experiment, the x motion may be hindered by an unknown force, maybe work from the surroundings, which wasn't accounted for. As we stated, there was no surroundings. So is the energy principle satisfied? In this case, for the energy principle to be satisfied, there must be no work done on the system by the surroundings. So that would mean that W has to be equal to 0. As a result, delta E must also be equal to 0. So if delta E, hypothetically, if delta E is 0 throughout the entire experiment, then the energy principle must be satisfied.